Well, first of all, good evening, ladies and gentlemen. As you all know, my name is Carl Jackson, and I'm from Manukau Institute of Technology. I cannot take sole responsibility for this project, as I have a partner in crime, my colleague Mr. Pinto. Together, we have been working on this project under the supervision of Charles Sweeney, who is the programmer for the Bachelor of Engineering Technology degree at MIT. Now, if you were to ask any Kiwi and living in New Zealand to name the two biggest cities in the last 3 years, they would name the earthquakes in Christchurch and the Paipura mine incident. Both of those incidences utilised the use of search and rescue robots. Now, what are we doing differently that all these robots aren't doing already? Well, we are wanting to test some technology and be able to create an autonomous search and rescue robot. One that can go around searching by itself without the need to be controlled, but with the ability to be able to be switched to manual control for fine precision. And by doing autonomous, we want the robot to be able to identify a human by itself without the need for a human operator to identify. And from there, we wanted to be able to create a network of robots. So to have 5 robots under the supervision of one operator instead of 1 robot per operator, just to be able to add extra resources to the search and rescue effort. And from the way we've tackled this project, we wanted to be able to do it in a modular-based design, that the modules can then be implemented on a series of different search and rescue platforms, i.e. aerial search drones or marine vessel drones. So, MITE, we call it MITE because it's the Manukau Institute of Technology Engineering and Search and Rescue Robot. Now, this is not a robot that we would put out into the field. It is purely a platform for us to be able to test the technology that will be involved in human identification and autonomous driving. And so, by being modular, it can also be adapted to fit the scenario that is required. In the Paipura mine, GPS would not be an option to be used, and so therefore GPS would not be included. But in the bush mountain area, GPS would be highly useful to be able to track the location. So, the way we went about it, we decided to build the prototype robot, so using VEX parts, which were at our disposal. Then the next step was to look into PIR sensors, passive infrared sensors, and ultrasonic sensors. These would be used to help navigate the robot, and if the Kinect didn't pick up a human, and a PIR sensor did, it would then create turn the robot to be able to focus on what the PIR sensor picked up. Next was to work on the Kinect itself, and this was the big one. This was where a lot of the technology we've been investigating lies, and I will go into further detail into that later. And then we also looked into GPS, and then the final step was to integrate it all together into what you see before you. So the architecture we decided to use, using VEX as a platform, we were able to use what we call the VEX Cortex, which is the main processing unit. That in itself can have 8 motors and 12 digital input-outputs, as well as 8 analog input-outputs. So we decided to use the ultrasonic sensors in the PIR to talk straight to the processor in terms of navigation, and any required information that the central processing unit needs would be transferred using serial to an onboard either laptop or embedded system. An embedded system would be better, but for what we had to use, we were using a laptop. And the laptop or embedded system would use robotic operating system. This would do the algorithms that would be used to process the images from the Kinect, and I will describe what the algorithms they are further on in the presentation. Finally, depending if it was outdoors, there would be a GPS, and both information, video feed, would be sent over Wi-Fi to what we have a base station where there will be a laptop connected to that. So first of all, VEX. VEX was simple, it's an easily constructible, and it's easily constructible design, and the ability to rapid prototype is very useful for what we were trying to do. Quickly looking at the sensors, we've got passive infrared sensors. Now this works, what we got it to is approximately 2 meters, even though they say it's got a range of up to 5 meters. But this detects motion through the difference in temperature as well from the infrared radiation. And also the ultrasonic uses a 3 centimetre to 3 metre range. That's for the object avoidance during the autonomous mode. So a closer look at this diagram, you can see that obviously a human that's been trapped in the bush would be stationary, but by the robot moving, it creates that motion that would go past the human, creating that passive infrared, and that's when it will trigger the robot to turn so that the Kinect could focus on it. Now we get to the actual Kinect. The Kinect comes with two cameras, RGB, and an infrared depth finding camera, both 640 by 480 pixels at a frame rate of 30 frames per second. And here you can see an image from the RGB camera and the depth finding camera. The colours that you can see show the different depths that is being processed, orange being closer, blue being further away. And using ROS it gives us the ability of having algorithms, libraries, drivers that for robotics is very useful with the Kinect. Here's the algorithm that we use. We used Honk initially, and Honk, what it does is it looks at the gradient around the edge of the test image, and then using support vector machine, the next set of algorithms, we are able to classify whether that image is human or not. So here we are detecting the gradients around the edge, and then classifying that until we get the shadowy figure here, which then decides as a human. Now this algorithm can be trained, so at this point it's been trained to detect humans in an upright position, but it can be trained using multiple images that you feed it to detect humans in different positions. At the moment, no one has used it to detect humans lying down, and so that is something that we've been working on ourselves, as that's what most of our search and rescue victims would be in a position of. And finally, using the GPS, we decided to go, after looking at multiple options, to use something that was really available to us. We're using the iPhone GPS with an app, GPS to IP. This iPhone software enabled us to be able to push out via Wi-Fi and push out the actual coordinates of where it is. This is something we struggle with as iPhones very blocked off, and they don't normally like pushing out information such as GPS location. But working around it, we're able to get the coordinates into a text file, and then we can then view it on the map using Google Maps applications. We decided to use KML format for the GPS, as this is easily usable on Google Earth. We looked at using NMEA standards, because NMEA we can get a whole lot of different information, velocity, altitude. We decided to keep the basics for now. Finally, the integration. Here we have in front of us an ultrasonic with the Kinect, a PIR sensor, another ultrasonic. We're going to put on for tonight 2 more PIR sensors, but we haven't got around to adding the 2 extra ones. This would have covered the robot in all directions to be able to identify any human that the Kinect couldn't quite see. And here we've also got the iPhone, which sends a signal over Wi-Fi, which my laptop is receiving. So where to next? We're not really finished with this project yet. We would love to see further that the improvement of the sensor and image detection. With a bit more training, we can get the image, the Kinect picking up people in different positions. Also with the Kinect, we have the ability of 3D mapping, which would be perfect in terms of the Pipe River Mine, being able to map where the robot has been, and that's why we've also got shaft encoders to tell the distance that it's travelled. And that way, search and rescue people, when they were ready to go in, if they got the all clear, would have known exactly how to get there using the mapping of the robot. Also, utilising Kinect microphones, there is a 4 microphone array on Kinect, which we would like to see for sound triangulation. If someone was in a bush screaming out for help, the Kinect should be able to determine exactly the angle that that sound is travelling from, and then to position the robot to travel to that. Also, networking the multiple robots together and to expand aerial and nautical robots. At the conclusion, what we've done is prototype robot, PIR sensor, ultrasonic GPS, and the Connect detection algorithm. Further investigation required is the Connect drivers on an embedded system rather than a laptop, real-time video feedback over the Wi-Fi, and the teleoperation of being able to using the video feedback as well as an online user interface that would be set up to monitor 5 robots at once. And so because this is a combined project, I will ask my associates, Lisa Pinto, to come up and help with any questions that you've got. Yes.
Could you explain a PIR sensor?
Yes, Lisa.
This was my area of research. PIR sensor is the same sensor you actually use in your security systems at home. The difference is it's a passive sensor. So what it does is it doesn't actually emit an IR signal, but it actually only accepts IR signals. That's why it's called a PIR sensor. If we possible to go back to the slides? To the big screen one, because we're using off-the-shelf platforms, what it basically does is all objects mostly get a radiation signature, basically. Either deflects it or actually reflects it or either radiates it. When a human mostly passes by, because that's the signatures mostly you're going to be looking at, the change in IR signatures is what triggers it, basically. And that's why you get that pulse over there. Does that answer your question?
Thank you.
Yes.
What was the moving speed?
We're concentrating too much on the speed of the actual robot. We haven't actually measured the rate of it, but we are actually available to give a demonstration at the end if anyone was more interested. External to the presentation, we're happy to show what we've done. And you can see it moving then. The thing to remember is that this robot was just a platform to test the technology. We weren't actually going to implement this in the field, but rather the technology invested on it would be what we want to implement in the field. I mean, this would be a perfect partnership for Joel if Joel created a contour robot.
In terms of the system's functionality, how does it compare to what is currently being used, like what's available overseas, for example? Is it further advanced?
I mean, it's, to be honest, with the technology, because there's only, with a non-large EV camera, you can't actually look into the dark spectrum of things. So if there's a dark or low light image, you can't really use it. But with the Connect, because it's got the IR sensor, you can actually look at the dark side of things. So if it was a nighttime vision, it would still detect a human. And that's basically where most of the search and rescue robots have been looking at right now, from what I've researched. A lot of it has been also for 3D mapping, so not many robots are there that actually detect humans while the robot's running. So it's a new research area we're looking into, basically. It's going to be feasible or not.
The key to it is being able to have this robot by itself and take the best
So it frees up resources.
How are you communicating with that robot?
We're communicating at this stage using serial UART to an onboard laptop, which we were hoping to have an embedded system with Panda board, but due to driver issues it hasn't been able to work. And from there, send signal over Wi-Fi. We have seen, and this will be something we will investigate further, is robots that have been able to have Wi-Fi expanders on the back that can travel to the edge of its Wi-Fi, drop an expander, and then be able to travel on further. And that's the technology we would want to implement to be able to increase the effective range of the robot.
What is the cost of the robot?
Sorry?
The cost.
The cost is minimal at this stage. The Connect itself is $200. It's or less than $200 in store. The ultrasonic sensors we've been able to pick up really cheap. And in fact, we've had our supervisor supply them to us for free. So it's the cost. We're like Joel. We're trying to keep costs at a very bare but looking into the technology rather than the robot itself. Great, thanks guys.